Hello. So today I'm going to take, my name is Clarence John Mary. Today I'm going to take you through this presentation of learning integral operators via neural integral equations. So we are going to go through a structured review of the concept, methodologies, and applications. So in my first slide here, we want to bring across the background and the problem statement. So in many scientific fields like physics, fluid mechanics, maybe brain dynamics, systems in there exhibit long distance and non-local dependencies. When I talk about non-local dependencies, this means I'm to give an example of a graph. Here it means we have a point on the graph uh, and the relationship or the factors that affect it may not be from the points that we can relate closely to that point, but points that are far away from it. Maybe if it's time, let's say if there is a point for today that is representing information for today, then maybe we have to refer to another point of last week, something like that. So that's what non-local dependencies mean in this case. This means that the interaction within the system can affect distant parts over time and space. Traditional methods like ordinary differential equations and partial differential equations struggle to accurately model such complicated behaviors. So in this paper, they propose two solutions, neural integral equations and attentional neural equations. These models help with this problem that I've stated above. Uh, these are powerful approaches because they do not require an explicit formula to describe the system dynamics. The models learn how to approximate complex interactions using second-kind integral equations. We have first-kind integral equation and second-kind integral equations. So these solutions use second kind since they are more stable. This integral equation is crucial for maintaining numerical stability throughout the computations, as we'll see later. So this is the equation that the processors use. So next up, we shall talk about the architecture, the neural network architecture, and multi-layer perceptrons. So here we have the role of multi-layer perceptrons. They are used to approximate the non-integral operators. Then the layers can approximate a wide range of integral operators. Then the deep networks also improve accuracy and learning capacity. So when we go to the architecture itself, we can see that the input layer receives discretized time series data representing observations from the system. So it receives data from the system. Then the hidden layers, they are the ones responsible for implementing the integral operator, which is refined through an iterative process. Then finally, the output layer produces functions, approximations that match the dynamics of the observed data. One of the key innovations I got was that was the integration of self-attention mechanism, which is inspired by transformer models commonly used in natural language processing. Self-attention replaces traditional integration techniques, allowing the model to process higher dimensional data more efficiently. Yeah, so that is it for this. We go to the activation function and the learning paradigms. So here, how is learning achieved? That's the idea we may want to figure out. So from what I gathered from the paper, it is reasonable to see that ReLU, rectified linear unit, is used to handle non-linearities effectively. it prevents the issue of vanishing gradients, a common problem in deep learning. Additionally, functions like the sigmoid or Tana, that is TNH, might be employed for bounded approximations. Yeah. In terms of learning paradigm, the models use supervised learning. So supervised learning, that means we have test data and training data. This means they are trained on observed data and the goal of minimizing the differences between the predicted and actual dynamics. The model adjusts the integral operator. It's learning to achieve this feat. Self-attention in ANI enhances the model's ability to represent complex patterns by focusing on relevant parts of the input without explicit labels. So it shows you that as this data is going through these stages, ANI enhances the model's ability to focus on the right things so that it's able to give us the right predictions. Error correction and optimization. Here we are looking at the techniques. Maybe the paper was showing us that backpropagation gradients to update neural network parameters, then gradient descent. Iterative updates refine the learning. Okay, this I've just already talked about it. I've talked about all this. Maybe if I go to the benefits, it ensures stability and improves convergence, meaning these techniques enable you to do the analysis of the data, then you're always moving to the one solution, converging to one solution that is almost, I say, at a high percentage of being correct. Then reduce errors in approximating non-local dynamics. So as I told you what non-local means, so it removes the errors of approximating such dynamics, then makes the model robust to variations in input data. So if they are different, there are varying kinds of data that you're inputting into this model, it is able, since the model is robust, it's able to give you the right stuff. So applications, as I told you, we use it in brain activity modeling, physics and engineering. So here I'm just showing you a few examples, like functional MRIs, then captures long-range neural dependencies more effectively. In physics, it does the Navier-Stokes equations, then Lotka-Volterra equations, among others. Then when it comes to performance, as I had already talked about the other integration, traditional integration methods that we are trying to solve, it's their issues here. ANI outperforms existing models, and models like the FNOs, LSTMs, and vision transformers, then captures non-local dependencies better than fixed grid numerical methods, then demonstrates superior accuracy in learning dynamic systems from data. So yeah. So in conclusion, those two methods that the paper provides us, from the paper's perspective, they are novel approaches to learning integrate operators in deep learning. Then the self-attention that ANI brings in enables efficient high-dimensional learning. Then the second kind, integral equations, ensure better stability and numerical feasibility. I gave you the difference between second kind and first kind. The second kind is more stable and what? The first kind integration. So it, in the long run, it even helps us get this better stability and numerical feasibility. Thank you.